Good morning, everyone. Today, we want to continue our discussion on queuing models. Last time, we considered a situation where we have multiple servers with infinite calling population and infinite queue capacity. Today, we want to consider a scenario whereby we have a restriction in the number of entities that can be accommodated on the queuing model. That is, a finite queue capacity and an infinite calling population. Here, we want to start by considering two fundamental parameters in queue models. First one is the P naught, and we can calculate it as 1 plus the summation of a raised to power n over n factorial plus a raised to power c all over c factorial into 1 minus a over c raised to power n minus c plus 1 all over 1 minus a over c all raised to power minus 1, that is 1 over all of those equations written here. Now, C represents the number of servers that we have on this queuing model, and A represents lambda over mu. Here, we are not using rho, because rho here will be lambda over mu c. Okay, we take note of that. Then secondly, we will calculate the number of entities that are waiting on the queue, that are waiting to be served, represented by LQ. This is equal to rho raised to power c plus 1 multiply p naught all over 1 minus, c minus 1 factorial into c minus rho all square, multiplying 1 minus rho over c raised to power n minus c plus 1 minus into bracket n minus c plus 1 into bracket 1 minus rho over c multiply rho over c raised to power n minus c. Now to put this into use, we want to consider a situation where we have, as an example, n to be equal to 7, that is the number of entities that can be on the queue equal to 7, and lambda arrival rate to be equal to 10 per hour, service rate to be equal to 6 per hour, and the system having 2 servers. Here we'll calculate P naught to be equal to 1 plus summation of n equals to 1 to c into all of these other equations here like we have stated. When we substitute the values for all of these parameters, we'll have it as P naught to be equal to 1 plus 5 over 3 plus 5 over 3 all squared over 2 factorial. Here, A is equal to lambda over mu, which is 10 over 6. When we divide through by 2, we have it as 5 over 3. That's why we have 5 over 3 here, plus 5 over 3 raised to power 2 all over 2 factorial, since C is equal to 2. Then multiplying 1 minus 5 over 3 all over 2 raised to power 7 minus 2 plus 1 all over 1 minus 5 over 3 all over 2 all raised to power minus 1. When you compute this, you're going to arrive at 1 plus 1.67 plus 1. So generate 1.389, and all of this becomes 0.6655, and the numerator becomes 0.167. And by the time you calculate this, you're going to have 1 over 8.205, which will give us 0.1218. So this is the P naught, that's the probability of the system being idle. Then if we want to also calculate the probability that a person who comes will get a server, that is, the person who comes will not just have to wait, will not wait for on a queue, but just enter straight to the system. That will be equal to P naught plus P1. That is, a person will get a system or server directly if one, if the two systems, it's either these two systems are idle or one of the systems is idle. That is to say, P naught plus P1 will represent such a scenario. Now, this will be equal to P naught plus rho P naught because P1, as we have mentioned earlier, is equal to rho P naught. So this is going to give us 0.1218 plus 5 over 3 into 0.1218. This is going to give us 0.343249. Then also the probability that there will be no queue. Probability that there will be no queue, the probability that either one of the system is, either the two systems are idle or one of the system is occupied or the two systems are occupied by two customers that are in the system. So in such a case, we have it to be equal to P naught plus P1 plus P2. This one will be equal to P naught plus rho P naught plus rho square over 2 multiply P naught. So when you substitute the values, you're going to get the answers for that. Now I'm going to leave this as exercise for you. You have to provide 1, 2, 3, 4, 5. The answers for these 5 parameters. That is the length of the number of customers waiting in the queue, the number of customers in the system, probability of n customer in the system. Remember, n here is equal to 7 now. Then you calculate the lambda effective and the waiting time in the system, the number of time or the amount of time that a customer will spend waiting on the system. So with this, we'll come to the end of queuing models. We come to the end of the discussion on the behavior or the performance of queuing systems or queuing models. Thank you for listening. Next time we'll continue from the next topic, random number generation. Thank you.